Hi, class. So what we're going to talk about now is acids and bases. And generally, what we want to think about is this bottom statement. An acid is a proton donor, a base is a proton acceptor. Now, we're actually going to see there's a few different types of acids and bases. So Arrhenius acids and bases are essentially acids and bases in water, right? And so the way that works is if you put a strong acid into water, instantly that water molecule is going to pick up that proton and make H3O plus, so hydronium. Hydronium is your acid source in water. So no matter what the strong acid is you put in, what we're actually going to measure is how much H3O plus you produce. It's still generating an H plus, right? And so a proton, right? So remember, a hydrogen without its electrons is a proton, is what we're looking at for our acid, right? So it's our proton donor. So as soon as we add a proton in, it's going to make a hydronium ion, which is this H3O plus. A base in water is just hydroxide. And the reason hydroxide is our base is it's going to be the molecule that picks up an H plus, right? If you notice, the difference between this one is to get to water, it's missing a hydrogen. This one has an extra hydrogen, right? So in acids and bases in water, we're typically talking about hydronium, so H3O plus. In basic solutions, it's hydroxide in water. It all comes back down to this idea. You have to have a molecule that can donate a proton, right? In water, it's H3O plus. In organic chemistry, there's a ton of different molecules that can donate a proton. And the more acidic it is, it means the better it is at donating this proton. A base is anything that can accept a proton. So the better you are at accepting that proton, the stronger the base. Right? And so that's what we're going to look at today. A couple more terms. So our conjugate acids and bases is just relating the groups through the equation. All right, so if we look at the molecules down here in the bottom, they're in an equation going forward. So we're going to take our acid, so HCl, so it's a really strong acid. So HCl, so hydrochloric acid, is going to take that hydrogen and we're going to donate it to water. So in this case, water is our base. Water isn't one of those molecules that can be both a base and an acid. In this case, it's going to serve as a base. So we're going to take this proton and put it on water. So that's what we see over here. We've made hydronium, so our H3O plus. Our chlorine has lost that hydrogen. All right, so now it becomes a base. Right? A very, very weak base, right? So the stronger the acid is, the weaker its conjugate base is. And so that's exactly what this conjugate pair is. It's looking at the molecule after the reaction. So if my molecule starts off as an acid, then it becomes a base. If it started as a base, it becomes an acid. And they're all related by the transfer of this electron. So we're going to, or sorry, this proton. So we add that extra proton over there. And the reason we're going to call this our conjugate base is acid-base reactions can go in reverse. So this one, in theory, could pick up a hydrogen and go back to HCl, right? So it can go back to HCl. And so this is how we're going to go back and forth from. So our conjugate base is just what the acid looks like once it's donated its proton. Our conjugate acid is just what the molecule looks like once it's picked up the proton. Big thing to highlight here, acid-base reactions are just the transfer of a proton. Right? And so remember, a proton is a hydrogen that's lost its electrons. Right? So one thing I'd really highlight is that a proton is just H plus. And so a lot of times we'll actually use H plus as our generic symbol for an acid, right? So sometimes when I get lazy, and actually a lot of us chemists do it, we'll just write H plus as a generic symbol for we need some acid to kickstart this reaction, but we don't really care what that acid is, right? Conjugate base acid pairs are just this, what we've shown. What's the linking of these two molecules? One thing that we're going to see is how does that proton move? So this is really important, and I know it seems a little trivial, but we always show the electrons grabbing the atoms. Right? So it's these electrons that are going to reach out and grab that hydrogen, right? So it's that electrons that are going to pull that hydrogen off. We never show the arrows where the atom's going, but more the electrons getting that atom. So in this case, ammonia is my base, and we need some source of electrons to pick up that proton. So this lone pair here is going to reach out and grab that hydrogen, and we're going to push those electrons on the oxygen. Now remember, if it's the double-headed arrow, so kind of a traditional arrow, it means 2 electrons. So these 2 electrons are grabbing this hydrogen. And that's actually, and let me highlight this in green, this arrow turns into this bond there. Right? And so that arrow is what makes that green bond, right? And we grab that red hydrogen. These electrons from that bond get pushed onto the oxygen. And so let me just highlight that in a different color. So maybe orange. So this arrow tells me that we've created those 2 electrons. Right? And we didn't necessarily create them, but we took them from being a bond and put them right onto the oxygen. All right. So if we're looking again, this was my acid and it was a proton donor. Here's the proton we donated to this molecule. So this was our proton acceptor. Here's the proton accepted. All right. So this would be my acid, my base. Now on this side, you can pause the video and write down which would be my conjugate base and my conjugate acid. All right, how'd you do? So this one is my conjugate base, right? Because it has the negative charge, it lost that hydrogen. And this is my conjugate acid, because now it has this extra proton that we can donate. Right? And so I know there's a lot going on this slide. I won't expect you to remember specific pKa values, but you should have a general idea of what they mean. All right, so pKa is essentially a measure of how acidic you are, right? So it has to do with the dissociation constant of that proton, but in a much bigger picture sense, it's how readily does it give up that proton? How acidic is that molecule? Right? And so what you should commit to memory is the smaller the number, the more acidic, right? So as we're going towards 0 and even into negative numbers, you're gonna have your really strong acid. As the number gets bigger, right, you stop being an acid and it's really, really hard to give up that proton, right? And in theory, we can always rip off some proton. In practice, it gets really, really hard. So for example, pulling a hydrogen off of an alkane or an alkene tends to be pretty difficult, right? So once you start getting up here above 20, it's really hard to rip off that proton. And not that we can't do it, it's just really tough. Right? The opposite is once we do rip off that proton, they tend to be really strong bases, right? So the conjugate base tends to be really strong if it was really hard to rip off that proton. And that's because typically that means that molecule really wants to grab that proton again. If you're a really strong acid, it typically means you didn't care that you gave up that proton, so you don't really have any interest in getting it back, right? So they're typically the opposites. So when we talk about a conjugate acid base, the stronger the acid, the weaker the conjugate base. Right? The weaker the acid, the stronger the conjugate base. So they're always an opposite, right? If something's a really strong acid, its conjugate base is going to be really weak, right? And then vice versa. Okay. So again, I don't expect you to memorize all these numbers, but you should know that as the number gets smaller into 0 and then negative numbers, you're becoming a stronger and stronger acid. One of the things, for the most part, all acid-base reactions are in some equilibrium. Some of them, the equilibrium is so far to one side, we kind of ignore the equilibrium. Some of them are sit right in the middle and they actually go back and forth. Right? So equilibrium is always going to talk about which of these molecules are we seeing, right? So they're going to go back and forth. Right? And so that's what this arrow is telling me, is that we're going back and forth. What this arrow here is telling me is that it favors this side. So equilibrium doesn't mean that there's the same amount on both sides. It means that the rate of going back and forth has stopped, right? Or has hit a constant level, right? So it's just kind of at a nice point where it's a steady state. The equilibrium is always going to favor the weaker acid, right? So the reaction of the stronger acid is going to push towards the weaker acid, right? So here we're going to give up this proton, right? We're going to protate this amine and we're going to get this compound, right? So the ammonia. So this is just what we saw when we did the arrows. And since this creates the weaker acid, it's going to favor this side of the equilibrium. Right? So we still have a little bit of this in solution, but if we're looking at it, it's mostly this molecule. Okay? And so that stronger acid is going to be the one that kind of drives towards going the other direction, right? It's telling us we're going to go the other way because it's really readily to give up that proton.